Everyone. Yeah. Our group will present the prediction diabetic rate using logistic regressions. Here is the agenda, what we cover for today's presentation. Firstly, we will introduce the project overview and objective. After that, we will describe the dataset description, data preprocessing, and we will explain which model we use, and we will show the result and evaluation. After that, we will discuss the business implementation, limitation, future recommendation. We will show it. Firstly, we would like to talk about the project overview and objective. Diabetes is a growing global health issue. According to the CDC references, early detection can lead to better outcomes and reduce healthcare costs. In this project, we use a real data set from the Kigel datasets with the 48K records. Our goal was to use logistic regression to predict the diabetes and identify the most important risk factors like HbA1c, hypertension, and age. We then evaluated our model using accuracy, precision, record the F1 score, and confusion matrix and ROC cap. Okay, and after that, next one dataset description will take over by my friend Beatriz.
Okay, first we needed to give a look at our data sets, which initially included 100,000 records, and we needed to identify our target variable, which in this case was diabetes. And then we give a look and divided our variables into numerical and categorical variables. And the categorical variables, we only found two of them. One was gender and the other one was a smoking history. There were no missing values on this dataset, and there were found as well, like on this dataset, we had 58% of females and 41% of males only. Next, please. Then we were looking at our dataset and we found that in the initial analysis, the age were including of months, years old of people till 80 years old. And also we found that in the correlation matrix that age, BMI, HbA1c level, and blood glucose level were the four variables with more correlation with our target variable. Next, please. Then we needed to identify the outliers. Here, for example, we can see that the blood glucose level, we have three specific numbers of outliers, which are 260, 280, 300. And we also found outliers on BMI and HbA1c level. However, on the other one of main correlation, which was age, we did not find outliers. Next, please. Then we needed to do a preprocess on our data set, and we needed to make it cleaner. So we knew that we had a data set with months old of people or 3 years, and we also noticed that we had the values of BMI for these ages. So we needed to remove all of the ones under or equal to 17 years old due to they were incorrect classified with BMI, since these people are supposed to be classified with percentiles. So we remove all of this dataset. Then we removed all the outliers that we previously identified from the dataset, and we also removed the variable for never smoked to make it cleaner. And this gave us a total of 48,520 new dataset values. And then, even with all of this reduction, we found that 56% of the datasets were females against males, meaning that remains the same as females being a larger group on this dataset. Next, please. Then we needed to redo our matrix correlation, And then, even with the reduction of all these data sets, we found that HbA1c level and blood glucose level remain as the main ones with relation with our predict variable, which is diabetes. And then with these new data sets, we needed to identify new outliers in which we found for blood glucose level, but uh, they were a way less, only with one numerical value, and with HbA1c level, they were removed completely.
Okay, I will talk about the methodology part. We selected logistic regression for our model because it's ideal for binary classification, especially in healthcare. It's easy to interpret and gives a probability score. We use X and X minor to clean and analyze the data. We remove missing value, filter out patient under 18, and simplify some variables, which mentioned in the previous slides. For example, gender was encoded at 0 for female and 1 for male. Smoking history was simplified to no info versus others. We also standardized numerical variables. Then we split the data 70% for training, 30% testing. The model completed training after 90 iterations. We use the prediction process step by step. Here how the logistic regression model works. Firstly, we calculate the logics and score based on all variables and their weight. And then we converted that score into a probability using a Simon function. And then if the probability is 0.5 or higher, we predict the person has diabetes. Otherwise, we predict they don't. We use this to make prediction and compare them with actual outcome. Here is the detail step by step. Firstly, we use logics, after that Simon, and then we make the decision with the greater than 0.5. Yeah, 1 for diabetes, 0 for not diabetes. Here is the model result. Our top predictor was HbA1c level. People with higher levels had over 8 times the risk. Other important predictors were hypertension, heart disease, and age. BMI and blood glucose were also positively linked to diabetes. The confusion matrix also shows where our model predicted diabetes. We had 3093 true positives. These were people who had diabetes and were correctly identified. There were 1543 true negative non-diabetic individuals who were correctly predicted. But we also had a very high number of false positive. 43877 people were wrongly predicted to have diabetes when they didn't. Finally, only 7 false negative mean the model missed just a few actual diabetes cases. This shows the model is very sensitive but not very precise. The model was very sensitive. It correctly found almost all diabetic cases with a recall of 100%, but it had very low precision, only 7%, and false positive rate of 97%. So we use the RCCAF here to see how good the model is at separating diabetic from non-diabetic case. It's compared the true positive rate, true positive rate, how many real cases was catch with the false positive rate, how many were we wrongly predict as diabetic. A perfect model would be up in the top left corner. The more the car the top left, the better model. We also look at the area under the curve called AUC. Here not mentioned the AUC, but AUC or 1.0 means the model is perfect. But in our case, that might be too good to be true. Good may overfitting. We should try threshold tuning or use better model like decision tree or random forest to get the better results, better prediction. Okay, next slide we talk about the discussion. Fatima will take over it.
So for the discussion, the logistic regression model successfully identifies almost all actual diabetes cases, achieving a high recall of 99.77%. This makes a valuable tool for early risk detection. Additionally, logistic regression provides interpretability, allowing a clear understanding of how demographic and clinical factors influence diabetes risk. However, Despite the strengths, the model suffers from a high false positive rate of 96.6%, um, leading to a low precision of 6.58 percentage and a low accuracy of 9.55. Next is the business and healthcare implications. So, if deployed in a real world healthcare settings, this model would generate a large number of false positive cases of 43,877, leading to unnecessary medical tests, increased healthcare costs, and potential anxiety among patients. Overdiagnosing non-diabetic individuals could strain healthcare resources and reduce trust in predictive screening models. So, to ensure practical usability, a better balance between recall and precision is necessary. Refining the decision threshold or exploring alternative classification models could improve the model's reliability and clinical decision making. Next, for the limitations and future improvements, several refinements could enhance the performance and practicality of this model. One significant improvement would be threshold tuning. Instead of using a default P is greater than or equal to 0.5, adjusting the threshold to P is greater than or equal to 0.6 or 0.7 could reduce false positive and improve precision. Additionally, exploring alternative classification models such as decision trees, random forest, or support vector machine (SVM) may provide better trade-offs. Future improvements could involve feature engineering techniques such as removing high correlated variables, testing interaction effects, or incorporating additional clinical indicators that might enhance the predictive accuracy. Addressing data imbalance issues or oversampling minority cases or using weighted classification techniques could also lead to a more robust and balanced prediction system. So, for the conclusion, I will turn over you to Win.
Okay, to sum up, we use logistic regression to predict diabetes using clinical and demographic data. The model was great at finding diabetic case, but also make a lot of false prediction. Because of that, it's not ready for medical use just yet. To improve it, we recommend adjusting the probability threshold, trying better model like random forest, and refining which feature we include. With this improvement, the model could become a powerful tool for early diabetes detections. Here is the reference list today, what we use for today's presentations. And next, where Beatriz will show our contribution list.
Here we show overall our contributions from Win, from Fatima, and from myself, and we all share responsibility for all of these steps that are shown. And on the following, we want to say thank you, and that will be all.
Thanks, everyone. Bye-bye.